Hello everybody. In this video, we'll learn how to calculate double integrals over circular regions. Now, in the previous video, we learned how to calculate double integrals over general regions, where the boundaries of the region in the xy plane were determined by functions. And we could use that technique, but for circular regions, it can become complicated pretty quickly. So we'll learn a different technique which can be used to make these kinds of problems easier. So let's consider integrating a function z is a function of x and y equal to 3x plus 6y plus 2. And let's say we'd like to integrate it over this region, the unit circle, which has equation x squared plus y squared equals 1. Now, in theory, we could solve this with the techniques we learned before. Right? We could break this circle into two parts. We can take this equation of the unit circle and solve for y. Subtract x squared from both sides and take the square root to solve for y. When we take a square root to get both solutions, we have both a positive and a negative solution. Y equals positive square root of 1 minus x squared. That gives us the top half of the circle. Y equals negative square root of 1 minus x squared. That gives us the bottom half of the circle. And the x values, well, this is a unit circle with radius 1. So the boundaries on x, the numbers, will be x equals negative 1 to x equals positive 1. So there are our boundaries. X goes from negative 1 to 1. Then y goes in between these two functions. So we set up a double integral that we would need to solve to calculate the volume. Right, so as before, I want to keep the y on the inside, and I'll put the functional boundaries of y here. And here's the function we're integrating. And we first have to find an antiderivative of this function. That's not too bad. The antiderivative with respect to y of 3x is 3xy. Antiderivative of 6y is 3y squared. Antiderivative of 2 is 2y. And then we have to plug in these functions for y. And you will get some cancellation, specifically when you square these. Those terms will cancel out. But in the 3xy and the 2y, when we plug these in and subtract, do a dot, dot, dot. I won't bore you with too much of the algebra. You'll end up with this expression that you need to integrate. This is doable. It's a little bit tricky, but doable with techniques you learned in single variable calculus. For example, to integrate this first function, you would want to use u substitution. You could let u equal 1 minus x squared, in which case du is negative 2x dx. You could use that to substitute away this x, leaving you with a square root of u and some constant, which you could simplify and integrate. So that's doable. This other term, you can't solve with a u substitution. You can solve with something else called a trigonometric substitution. In this case, you could let x equal, say, sine theta, in which case this expression would simplify. You'd have 1 minus sine squared theta. That's cosine squared theta, and then the square root of cosine squared leaves you with cosine. But then you have a dx you have to worry about. But there's a trigonometric substitution. You probably learned about that process in a previous class. This is solvable. Not necessarily pleasant, not like the things we've been doing so far. So in this video, I want to show you a different way you can go about solving equations like these to avoid the use of this kind of substitution. It turns out the easier way to go about this is by using polar coordinates. They come up a surprising amount of time. We previously discussed them when we were talking about things like the chain rule, and that it gives us a new way to think about certain kinds of derivatives. So polar coordinates turn out to be very helpful for this kind of problem as well, because the equation of a circle is simpler in polar coordinates. Right, so hopefully you recall in polar coordinates, Right? There's two ways to specify the location of a point, in terms of x and y, or in terms of r and theta. R refers to the distance from the point to the origin, and theta refers to the angle between this vector, or this ray, and the x-axis. And using some right triangle trigonometry, right, you can actually come up with formulas which allow you to convert between x and y, r and theta. For example, sine theta is equal to the opposite side divided by the hypotenuse. So sine theta equals y over r. Cosine of theta is defined to be the length of the adjacent side divided by the hypotenuse. So cosine theta is equal to x over r. Right, so keeping that in mind, in order to solve one of these integrals involving a circular region, there's 3 steps. The first step is to convert this function, f of xy, into a function featuring only r and theta. In order to do that, we know that x equals r times cosine theta. So every place you see an x, replace it with r times cosine theta. Every place you see a y, again from over here, we know that y is equal to r times sine theta. So replace y's with r times sine theta. It's the end of step 1. Step 2, we want to convert the bounds of this region to values, formulas involving r and theta. Remember, r refers to the distance from the origin to a point, and theta refers to the angle around the origin. And this is where the technique really shines. It turns those complicated expressions, right, involving those square roots, into something much simpler. So for the unit circle, r ranges from 0, the center, to a distance of 1 in all directions. So r, the boundaries on r are from 0 to 1, all the way around. So that's our first boundary. Now how far around the circle do we go? Well, in this case, we make a full revolution. Right? So theta goes from 0, so all the way up to, right, this is pi over 2, pi, 3 pi over 2, all the way to 2 pi. So theta does a complete revolution. One thing which is very important, we need to use radians. We might think in degrees sometimes, it might be more intuitive, but stick to radians for doing these calculations. So the boundaries for theta are 0 to 2 pi. And that is the bounds for this. Right? Much easier than the ones we saw before. Now, this kind of r theta approach is good for anything which really involves arcs and circles and shapes like that. As 2 more examples, let's say we have this shape right here. Looks kind of like a ring or a donut shape. Right? In this case, right, we're interested in this region shaded in red. Right? The radius r starts at a distance 1 from the origin and continues to a distance 2 from the origin. Right? So from 1 to 2 along every point. And in theta, well, we go all the way around the origin. So theta once again goes from 0 to 2 pi. And so a shape like this, you could also capture the pretty easy set of inequalities in r and theta. A shape like this, right, this looks kind of like a slice of pizza or a wedge of pie. Right, in this case, right, this is the shaded region here. The values of r, we start at the origin, so r starts at 0, goes all the way out to a radius of 1 at all points. So r goes from 0 to 1. But in this case, we're not going all the way around a circle. Here, theta starts right here. Right? This would make an angle of about pi over 4 with the x-axis. Theta ends, and in the direction of going straight up, and that forms an angle of pi over 2 with the x-axis. So here, for a slice of a circle, the bounds of theta, in this example, are pi over 4 to pi over 2. And so again, step 2 covers a whole bunch of different possible cases. We'll see examples of all of these. And then, step 3, we need to replace dy dx. With what? This is a little bit, well, it's not hard, but I want to make sure we understand why we have to make the substitution that we do. As a hint, it's not just dr d theta. To really understand why we have to make the substitution that we do, we have to go back to the first idea. Double integrals are based on Riemann sums. So the double integral of f of xy dy dx, really that comes from taking a limit of a double summation of terms that look like this. This represents the volume of a box. We can think of it as the height times the width times the depth. We can also think of it as the height times the area of the base. And I'd like to think of it in that way. So the volume of the box is the height times the area of the base. The height is f of xi, yj, where this corresponds to points inside the base. And then delta x and delta y, those are the spacings between the sample points, xi, and the sample points, yj. Now, when working with polar coordinates, we could start with a similar Riemann sum approach, but because we're not working with x and y, we're working with r and theta, we're not dividing up along the x and y axes. We're dividing along the r direction, so along the radius, and we're also dividing along the theta. As we go around, we have all these different values of theta. So we're still thinking of this as the base, and then there's some kind of a surface in 3 dimensions which sits above this base. Again, to calculate the volumes of these different shapes, it's still the height times the area of the base, but we need to know how to calculate the area of one of these shapes. How do we do that? We'll call them circular sectors. So as the number of divisions of r and theta increases, these are going to get smaller and smaller. And as you take a smaller and smaller arc of a circle, it becomes less and less curved. So these shapes will look more and more like rectangles, as you take the limit, as the number of radial segments and angular segments gets large. So we can calculate this area the same way we would calculate it if it were a rectangular shape. The area of this will be approximately the width times the length. In this case, dr, we can think of that as corresponding to width, but d theta, that's measuring an angle. It's an angle measurement, not a length measurement. So the real question is, how do we find the area of this curved part? We need to figure out the area. We do need to figure out the area of this region. To do that, it'll be the length of this side times the length of this side. So we need to find the length of this arc of a circle. And let's assume that the circle has radius r, and the angle, corresponding to arc, this arc passes through a total angle of d theta. Well, the length of an arc, of part of a circle, one way you could calculate that, you could calculate the total circumference of the circle, and then this piece of arc, this arc of the circumference that you want, figure out what's the percentage of the circumference corresponding to this arc. And so that'll be our calculation to find the length of the arc. To figure out any percentage, you need the part over the whole, the part we're interested in, that's d theta, and the entire circumference, that's measured in 2 pi radians. So this is the percentage of the circumference we're interested in. Now the actual circumference of a circle, that's calculated as 2 pi times the radius. Then when we multiply these things together, something very convenient happens. The 2 pi in the denominator here cancels the 2 pi in the numerator here. So what we're left with for the length of arc is the angle, d theta, times the radius, r. Right? So that's how long this arc is. This is r times d theta. So what's the area of the circular sector? It's approximately dr times r times d theta, which is typically rearranged to be r times dr times d theta, r dr d theta. So the conclusion of all this side investigation, in step 3, what do we replace dy dx with? We replace it with r dr d theta. Again, we need that extra r because the area of these circular sectors is calculated differently. Let's go back to the original question now. And let's see how much easier this is going to be to integrate. Right? We're looking for the volume underneath this function, 3x plus 6y plus 2, but over the unit circle. Originally, we had this double integral, which was a little bit complicated because of these bounds. But then, if we go through all the different steps, step 1, replace x with r cosine theta, replace y with r times sine theta. Step 2 is to replace the boundaries of the circle. Right? In this case, I'll always put r on the inside and theta on the outside. Right? For the unit circle, the radius goes from 0, the center, to 1, the boundary. And theta goes from 0 to 2 pi. Right? This region, the circumference, traverses all the way around the origin. Step 3, replace dy dx with r dr d theta. Right now, this r, we can go ahead and distribute that through here. We've got some r squareds and a 2 times r. Now, this is our function that we need to integrate. And this is much easier. This does not require a u substitution. There are trig functions, but it doesn't require a trig substitution. We just need to integrate this. So let's go ahead. Right, first, we'll do the inner integral. Right, so first, r is the variable. Treat r as a variable, which means theta is a constant. If theta is a constant, then cosine theta and sine theta are also constants. And so we have 3r squared times a constant. The antiderivative is r cubed times that constant. Similarly, the antiderivative of 6r squared times a constant is 2r cubed times that constant. And the antiderivative of 2r is r squared. We have to evaluate that on our boundaries for r, so from 0 to 1. I do love plugging in 1 and 0. So plugging in the 1 leaves us with this function. Plugging in the 0 leaves us with nothing. So now we have to integrate this function. In this case, theta is the only variable left. The antiderivative of cosine is sine, because the derivative of sine is cosine. The antiderivative of sine is negative cosine. Right? Don't forget that negative. And you find the antiderivative of sine. And then this expression we need to evaluate on the bounds of theta from theta equals 0 to theta equals 2 pi. And so we do need to know some trig values. So sine of 2 pi is 0, cosine of 2 pi is 1, and then, well, we just plug in the 2 pi for theta here, minus, now we need to plug in 0 for each of these, sine of 0 is 0, cosine of 0 is 1, and then plugging in a 0 for theta. I should get a bit of cancellation here. The negative 2 minus a negative 2, those cancel. Actually, all we're left with is 2 pi. Right? The volume over that circular base, but underneath that surface happens to be 2 pi. And since we're working with circles here, it's perhaps not too surprising to see pi in our answer. Let's do another example. Now, this is a very strangely shaped region. It looks like the letter C. C for calculus. I'd like to find the volume underneath this region. And this is the equation 5x plus 3y plus 7, which lies over this region right here. Again, since there's arcs of circles, right, this is a good time to use polar coordinates. I'm here, right? We're interested in this shaded region. It starts at the circle where r equals 3 and extends out to the circle where r equals 4. So the boundaries on r are 3 to 4. In this case, we only have the left-hand side, though. It's almost like half of a ring, right? Half of a donut. So in this case, the angle that we're starting at is pi over 2. It points straight up. Then we continue along until we reach the angle 3 pi over 2. And so those are our boundaries for theta. So we've got our boundaries and our function. We replace x with r cosine theta, replace y with r sine theta. 7 just comes down. And then dx dy becomes r dr d theta. Right, distribute through the r, and then do your integration. I'll do both those two steps at once. We'll wind up with the antiderivative of 5r cubed over 3 times cosine theta plus r cubed times sine theta plus 7r. We need to evaluate that from r equals 4 to r equals 3. And so plugging in some numbers, we'll get all sorts of fun-looking fractions until we're left with 185 over 3 cosine theta plus 37 sine theta plus 7. And then, well, we need to do this integral with respect to theta. Remember, the antiderivative of cosine is sine. The antiderivative of sine is negative cosine. And then we plug in the values 3 pi over 2 and pi over 2. In this case, there's a lot less cancellation because the function isn't as symmetric as it was before. In this case, once you add together like terms, right, we're going to get, see, negative 185 over 3 minus 185 over 3. That's negative 370 over 3. And then we'll get, see, 21 pi over 2 minus 7 pi over 2, that's going to be negative 14 pi over 2. I somehow dropped my over 2. There should be 14 over 2 pi, or that would reduce to 7 pi, so sorry about that. You might want to change that in your own notes. Right? And that is the answer for this one. Right? And I suspect that in this case, the answer is actually negative, which means that the majority of this solid lies underneath the xy plane. Now, I just do want to make a note right here. You might notice that we've been working with some very simple functions for integration. That's on purpose, right? In general, when we're working on problems like this involving circular regions, if we integrate something even slightly more complicated, right? Something like f of xy equals x squared plus 5xy. If we had a rectangular base, this would be no problem. Even if we had a base bounded by two curves, like we did in the previous lesson, again, no problem. But if we integrate something like this, when trigonometric functions are involved, we're going to get things like cosine squared of theta, or cosine theta times sine theta, and those are really hard to integrate unless you know all sorts of trigonometric identities to rewrite them. Things like double angle formulas or half angle formulas. In that case, we'd have to use those to integrate. And I'll assume that you had your fill and you had enough fun doing this in your single variable calculus course. And if you really needed to, you could look up those formulas. But in this course, we're focused on the idea of how things generalize to higher dimensions. Right? And I'm hoping that we'll get this idea across without adding in that layer of extra complexity. So we'll avoid this situation completely, dodging it. We're going to focus on these simpler functions which represent planes. Right? So you can visualize these types of volume problems over a circular base. It's kind of a cylinder with the top bounded by a plane. Right? So a standard cylinder with part of the top sliced off. Those are the kinds of calculations we'll do. Speaking of doing calculations, it's time to learn some math by doing math. So what I'd like you to do is integrate this function, 2x plus 3, It didn't include a y term because we'll just make this one a little bit simpler. But let's integrate this function over this region. Right, so this is going to be a quarter circle of radius 6. And so in this case, the radius, the r, goes from 0 all the way out to 6. Since we're looking at a quarter circle and it's positioned in the first quadrant, we start at the angle theta equals 0. Right, and going up to here, this is the angle theta equals pi over 2. Right, so you'll want to go ahead, set up that double integral, but in terms of polar coordinates. And since this function is even simpler, hopefully this will be even easier to solve, and see what you get for the volume. And that is the simplest way I know to calculate double integrals over circular regions. Thanks for watching.